Hello, students. So, as I speak to you today, I'm finally getting around to doing that video on the first set of homework that I assigned over environmental chemistry. So, chapter 2, which is problems 5, 7, 8, 9, 12, 13, and I think 15, 16. Okay, so let's start looking at those. So, we'll look at them each in turn, how we should be trying to solve them. Some of them are math related, some of them are a little bit more thinking related. So number 5 asks us if we have the gases from the wood burning stove contain 1.8% carbon monoxide at 65 degrees Celsius, and they want us to express this value. We want to turn this value into grams per meter cubed. Grams per meter cubed. So we have to convert some pressure units into like mass units. And the hint I give you is that, okay, first we're going to use ideal gas equation to find this in moles per liter, assuming one atmosphere of air, and then do some simple conversions to get grams per meter cubed. A little bit of a pain, but can be done. So, our first step here. Knowing that essentially you don't need this equation, but the idea that the pressure of a gas is equal to the pure, we don't need that at all. So the idea is that out of one atmosphere, 1.8% of that is going to be CO2. So 1.8% means we're going to have 1.8 over 100, or let's see, 0.018 ATMs. Now, the ideal gas equation is PV equals nRT. So to get molarity, we need N over V. So with that in mind, P divided by RT is equal to N over V. So we have a pressure, 1.8. R, and the units of atmospheres, 0.8206 ATM liters per mole Kelvin. And we need to turn 65 degrees Celsius into Kelvin, so adding 273 onto that is going to turn this into 338 Kelvin. So 38 Kelvin. So all this simple, I mean, it's not particularly hard per se, but all this little math right here, this just gives us a concentration. The 0.018 divided by my R divided by my T gives us a really small number, and that's fine. That's to be expected. So 6.4, we'll say 9 times 10 to the negative fourth moles over liters, or molarity. Now, we need to convert moles per liter into grams per meter cubed. To do this, we need to look up some conversions. 1 liter is equal to 10 to the negative third meter cubed. Another way to look at this is 1 meter cubed is 1,000 liters. And the molar mass of CO, the molar mass, is 12 from carbon and 16 from oxygen, so 28 grams per mole. So the sooner we get used to canceling units, the better off we are. So from this number, we're going to say times by 28 grams over moles, and that gets rid of that. And we're going to times by 1,000 liters per 1 meter cubed. Liters and liters. So I'm going to take my number, multiply by 1,000, multiply by 28, and I get something like 18.17 grams per meter cubed. And that is my answer for number 5. There's a little bit of math involved, but none of this math is particularly challenging if you know what you're doing. None of this math is new. It is all general chemistry 1 stuff. The only different aspect would be using the 1.8% to figure out a partial pressure of carbon monoxide. So that in itself is not supposed to be too bad. Now number 7. Number 7, a little bit trickier. Calculate the maximum wavelength of radiation that has sufficient energy to cause the dissociation of NO. So, and in what regions of the atmosphere would such radiation be available? Use Appendix B2. So with that in mind, we need to look up stuff on Appendix B2. We are not going to do that. I already have that value looking. However, you're basically looking up the dissociation energy. If you can find this reaction, you're looking up the energy associated with this reaction. So N plus O. B2, if I'm not mistaken, talks about the enthalpy, your enthalpy values. So your enthalpy values, to find the enthalpy, you're going to look up, okay, the enthalpy, the delta H of formation of this is 90.25 kilojoules per mole. The delta H of this is something like, I think, 472.7, and the delta H of this is something like 249.17. 249.17. So, the first step is find out what is the enthalpy of this reaction. What is the enthalpy? The enthalpy is always going to be products minus reactants. Products minus reactants. So with that in mind, you're going to say, well, 249.17 plus 472.7 minus 90 and a quarter. So doing that, just real quick, this is going to be highly endothermic because it's going to take energy to break and cleave this bond, and that's not super surprising. Something like 631.62 kilojoules per mole. So every mole of NO we are cleaving takes 631.62 kilojoules to cleave. Now, the next step is just turning this into joules per photon, because we want to look at individual beams of light, not moles of light. So there's a little conversion in here, but it's not really bad. To get this into joules, you're going to multiply by 1,000. So positive 631.62 kilojoules per mole. It's going to take 1,000 joules in 1 kilojoule. And because we also want this as an atom instead of a mole, we're going to use our friend Avogadro's number, which is 6022 times 10 to the 23rd atoms per, what? I already did it wrong. 1 mole over 6 0.022 times 10 to the 23rd atoms. See, this is why I write it out. I can easily see, okay, if moles need to cancel, I need moles up top. Kilojoules need to cancel, I got kilojoules down there. So, with that in mind, so 631.62, I times by 1,000, but then I divide by Avogadro's, 0.22 and 10 power 23. And I get how much joules do I need to break up one atom, one single atom. So we'll put 1049 times 10 to the negative 18th joules per atom, and that's also going to be joules per photon. Now, this middle step is the hard step. This middle step is the hard step. So this is an energy. Energy, we need to break this up. Well, we can relate this back to our light. E equals h nu, and then C equals lambda nu. You can do this separately or together. You can say, if I'm solving for lambda, if I want to solve for the wavelength right here, I can say that lambda is equal to C divided by frequency. And if I have energy and I want to solve for frequency, I can say energy divided by h is equal to frequency. So really, if I want to solve for lambda, lambda equals hc divided by E. hc divided by my energy. You can go slowly, you can go quickly, it doesn't really matter. You can do it in one equation, you can do it in multiple equations, it doesn't really matter. The idea is that we got, so H is a constant in joules per joule seconds. C is a constant in meters per second. So our frequency right here, if we calculate this, will be in meters per atom. So wavelength per atom that we need to cleave, or wavelength per photon that we need. So H, you can look that up, 6.626 times 10 to the negative 34th joule seconds, times speed of light, 2.998 times 10 to the 8th meters per second, all over my 1.049 times 10 to the negative 18th joules per photon, or joules per atom. Joules, joules, seconds, seconds. We're left with meters and photons. Now it's just a matter of plugging this in, not getting fat fingers and not typing in things wrong. 6.626 times 10 power negative 34 times 2.9, see, I already fat fingers on, 998 times 10 power 8, and divided by 1.049 and divided by 10 to the negative 18th. And I get a really small number, but this is in meters. If I multiply this by 1,000, I get this in millimeters. If I multiply by 1,000 again, I get this in micrometers. Multiply by 1,000 again, I get this in nanometers, 10 to the 9th. So this is 189.4 nanometers. Then if you look, where is that wavelength penetrate from the little chart, we'd say, oh, that happens in the mesosphere. Mesosphere is when we get that wavelength of light penetrating. But that is number 7. Number 7. So, now number 8. Number 8 reads as follows. The average distance a gas molecule travels before colliding with another, the mean free path of S, is a relationship that K, Boltzmann's constant, T, over the square root of 2 times the pressure times sigma C. T and P are temperature in Kelvin and pressure in Pascal. So pressure is in units of pascals. And Boltzmann's constant is a constant, 1.38 times 10 to the negative 23rd joules per Kelvin. And sigma C is the cross section of a molecule, meters squared. Calculate the mean free path of dinitrogen molecule at standard pressure and the Earth's surface standard pressure and temperature, 25 degrees. The mean free path of dinitrogen is something like 0.43 nanometers squared. What does this indicate about regarding the gas phase reactions in these two locations? Oh yeah, it's at the Earth's surface and the stratopause. So we're just doing it at 2 pressures and temperatures. Everything else is more or less constant. Everything is more or less. So at the Earth's surface, we're saying 1 atm, which is the equivalent of 101.325 pascals. Now, some people will know that conversion. Some of you may have to look that number up. I don't expect you to know it. You can look up the conversion of 1 atmosphere to a pascal, but that is the conversion rate. So this one, it's really just plugging our numbers in. Just watching our units. So joules per Kelvin cancels out the Kelvin. The big thing here has to do with the units. A joule is equivalent to a Pascal meter cubed. And we want a mean free path in, say, nanometers or micrometers. So that means we need to convert this meter cubed into something like nanometer cubed. Or we can convert this guy from nanometers into meters. However you want to do this, you got to do this. This is the one thing you got to worry about. You got to watch out for. Otherwise, you're not going to get the numbers quite right. So I'm going to convert my K into nanometers cubed. So 1.38 times 10 to the negative 23rd pascals meters cubed per Kelvin. And I'm going to say, okay, well, in 1 meter, there is 10 to the 9th nanometers. And I have to do that 3 times. So that means my 1.38 times 10 to the negative 23rd, and I'm going to times that by 10 to the 9th, times another 10 to the 9th, times by another 10 to the 9th, means my Boltzmann's constant in nanometers cubed is 13800. 13,800 pascals nanometers cubed per Kelvin. I know I'm running out of room, so I'm going to move to the next sheet. So, with that in mind, that in mind. We have S equals 13,800 pascals nanometers cubed per Kelvin times T, which will change, divided by the square root of 2 times my 0.43 nanometers squared times my pressure in pascals. At this point, this will simplify into a constant, and it's really going to be constant times T over P. So I can go ahead and solve that. What's that constant? And then just work from there. So I'm going to divide 13,800 by square root of 2, divided by my 0.43. And this is giving me, okay, we have constant 22,693.2. That's going to be pascals nanometers per Kelvin times T over P. So at the Earth's surface, T is 298 and pascals is 101,325. So when I multiply that by 298 and I divide by 101,325, you get the average mean free path is something like 66.74 nanometers. 66.74 nanometers. So a nitrogen molecule can move about 66 nanometers before it bumps into another nitrogen molecule. Well, what about up at the stratopause, right before if you look on the chart, at the stratopause, the temperatures at the stratopause is something like 271 Kelvin, and the pressure is something like 185.2. So you would have to look that up from a chart, but let's do it from those temperatures. So same thing, 693.2. We multiply by 271 Kelvin, divided by 185 and 20. 63.2 times 271 divided by 185.2, and you get something like a really big number, 33,206.6, which is 33.2 micrometers. So at the stratopause, nitrogen has to move a lot farther before it bumps into another nitrogen atom. It's almost divided by 6. That's like 500 times the distance, just about. So what's that going to tell us about reactions where you need collisions? They're going to be happening a lot slower up in the stratopause because it requires a lot more distance before the chance of bumping into another gas molecule. And so collisions are going to happen more slowly overall. A lot fewer collisions. With that in mind, that was 8. 8 was perhaps one of the trickier ones. 9. It's pretty much a lot of the same thing you did for number 7. Calculate the maximum wavelength needed to split up a dinitrogen molecule and a oxygen, basically molecular oxygen and molecular nitrogen molecule. The exact same work. The only difference is we have a different enthalpy. But if you can do that, if you could do number 7, you could do this one. It's the only problem The only difference is it's a little bit easier because the enthalpy of pure elements are 0. So we're just looking at, okay, what is the enthalpy associated with nitrogen? Well, nitrogen is 472.7, and there's 2 of them. So we double that. The enthalpy associated with oxygen is 249.17, and there's 2 of those. So with that in mind, the enthalpy of the nitrogen reaction would be 945.4 kilojoules per mole. And then we're going to have to times by 1,000, divide by Avogadro's number. 23rd, what does that give us? 45 times 0.4 times 1,000 divided by 6022. 23rd. That gives us 570 times 10 to the negative 18th. Doing the same thing, the lambda equals hc over E, and then we're going to times 10 to the 9th to get this in nanometers. Nanometers per 1 meter. So 6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th, all over 1.57 times 10 to the negative 18th times 10 to the 9th. So, doing that, it's pretty much straightforward at this point. 34 times 2.998 10 to the 8th times 10 to the 9th. And so you get, what's the wavelength? 126.5. 126.5 nanometers. What about oxygen? Oxygen, the enthalpy for oxygen is going to be, it's going to be 498.34. I'm going to skip writing all that stuff out, but 498.34 times 1,000 divided by Avogadro's number. That's going to be, that one's actually even smaller, 8.275 10 to the negative 19th joules per photon. Same steps again. 6.626 10 to the negative 34th, 2.998 times 10 to the 8th times 10 to the 9th. Doing all the same steps, you get, all said and done, 240.0 nanometers. And so, what does that say? We need a lot more energy to break that because this is essentially a double bond versus nitrogen being a triple bond. It takes more energy to cleave that than it does to cleave that. So, that one's reasonably straightforward, all things considered. Jumping to problem 13. This one is, if you understand how to do this, is actually really, really easy. Which of the following species are free radicals? O3, Cl, ClO, CO. You could draw the Lewis structures, but there's a way to bypass this. NO3 1 minus and N2O5. And you don't need the Lewis structures. You need to count what column, what group number are each one in, and if they have an odd number of electrons, they will always be a radical. So oxygen is in column 6, hydrogen is in column 1. You sum of them up, 7. So no matter what, when we make this, it's going to be a radical. So 1, 2, 3, 4, 5, 6, 7. Ozone, 3 oxygens, going to be 18. Even, it's not going to be a radical. Chlorine is in group 7. So with its 7 electrons, it can only be a radical. ClO, 7 plus 6, that's 13. That's going to be a radical. CO, 6 plus 4, or 10, it's going to be no radical. Nitrogen, 5 plus 6, it's got to be a radical, with 11. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N2O, there's 2 nitrogens in an oxygen. It doesn't have to be a radical. NO3, 5, NO3 1 minus 5 plus 6 times 3, but plus 1 for that spare electron means essentially, well, it's 24 electrons, no radical. N2O5, 5 times 2 and 6 times 5, 30. 40 electrons, no radical. So if you can get and see that odd number of electrons means we have a radical, that one is actually amazingly quick and fast compared to all the other stuff. Okay, 16 is a little bit more in depth, so we gotta spend a little bit more time. I gotta make sure we have space for that. For the reaction, NO plus ozone goes to NO2 and oxygen. It's a second order reaction. Second order reaction with we'll finish this one, and that's going to be the last one. Obviously, we're almost out of time. Second order reaction with the rate value constant. K is 1.8 times 10 to the negative 14th centimeters cubed per molecule seconds. Molecules seconds at 25 degrees. The relative concentration of NO is 0.10 ppbV. The ozone is 15 ppbV. Calculate these two concentrations in units of molecules per centimeter cubed. Calculate the rate of NO oxidation. Show how the rate law can be expressed as a pseudo first order in terms, and calculate the corresponding pseudo first order rate constant. So the rate equals K times NO times O3. So we need to do some quick calculations. ppBV is moles per mole total times 10 to the 9th. So 0.1 ppBV would be 0.1 times 10 to the 9th over 1 mole. So like whatever, actually sorry, x over 1 mole is going to be times 10 to the 9th is 0.1. So converting this, converting whatever our number is, you're going to get a really small number. Let's see, to do this. So essentially this is a nanomole. To do this, this would be 0.1 would be a nanomole per 1 mole. We need to convert this into molecules. So 1 mole is 6.02 2 times 10 to the 23rd moles per, molecules per mole. And we need to turn this number into a volume in centimeters cubed. This number into a volume in centimeters cubed. And the way to do that is, since this is a mole, N times RT over P is equal to V. So we can take that 1 mole and multiply by our R, our temperature at 298, and divide by a pressure. To do that, so we're going to say, we're going to times this by 0.08206 at 298 Kelvin over 1 atmosphere. And that's going to give us a volume in liters. And the last step is, there's 1,000 centimeters cubed in 1 liter, because there's 1 centimeter cubed per 1 milliliter. So 0.1 nanomoles times Avogadro's number. So times 10 to the negative 9th divided by 0.08206 divided by 298 divided by 1,000. And you'd get something like 2.463 times 10 to the 9th molecules of NO per centimeter cubed. I'm running out of time and I'm running out of room. Doing the exact same thing with our oxygen. 15 nanomoles, same steps, same exact conversion. You'd get something like 3.694 times 10 to the 11th molecules per centimeter cubed. I know I hate to rush this, but I gotta rush it. So plugging these guys in with our K's. So you're saying 1.8 times 10 to the negative 14th times 3.694 times 10 to the 11th times 2.463 times 10 to the 9th. All this is going to give us units of molecules per centimeter cubed per second. So it's 3.69 times 10 to the 11th times 2.463 10 to the 9th. And you get something like, I got 1.638 times 10 to the 7th molecules per centimeter cubed per second as my rate. That's my rate. Now, a pseudo first order says, well, if ozone is in much greater concentration, we're going to say K times ozone is more or less constant, and you'll make a new K prime constant. To do that, you're just going to multiply the K constant, 1.8, times 10 to the negative 14th, by my ozone, which is 3.694 times 10 to the 11th. And so you get your K prime constant as 6.649 times 10 to the negative 3rd, 1 over seconds, times my NO concentration equals my rate. So basically, the rate is just this times this, and we can figure out how fast this is going to degrade based on that. That's my pseudo first order rate. Now, I know I had to rush through this last little bit. I'm sorry, but that is the last problem. This is less of a problem that I expect of you, so not supposed to be not supposed to be one you worry too much on. With that in mind, have a good day.